Hi. Hi. Let's get started in about a minute here. Oh, I better mute that. Actually, that would be bad. Okay, so today is March 24th, 2020. This is the next lecture in Calculus 2 online lecture. But before I start yakking about math, let me say something. I want to say a little bit about our plan going forward with this class. So let's see here. The big thing that so there's a few big things that I want to just highlight. I guess the first big thing that I want to say is all of our everything that we're going to do in this class is going to be online. There's no in-person stuff for the rest of the semester. So this is very challenging. If you ever need to find resources like videos or handouts that I've created and have given out, you can go to our WordPress site. The URL should be readily available to you via email, for example. And just to be clear, what I'm using is the email that you have through school. Okay, so check your school email. We will be streaming here every Tuesday, Wednesday, Thursday, and Friday at 8 a.m. And afterwards, the lecture hopefully will be uploaded to YouTube, more or less immediately. That's what I'm hoping. I'm going to have these lectures go for about 50 minutes, just like a regular old lecture. And the big thing, I guess, is after every lecture, your assignment, part of your homework, is to before the day ends, write an email to me that answers a question that I'm going to pose to you during the lecture. Okay, so this is a way of making sure that you're actually watching the lecture, because lecture is a required part of this course and still will be, even whether or not coronavirus is raging or not. We're going to call these things post-lecture slips. They're going to be via email again. And the way that it's going to work is I'm going to send out an email after I'm done with this lecture, and I'll have links and things like that to the YouTube video, I'm hoping. And then you will watch it and then respond to the email that I send, okay, with your answer to the question that I'm going to pose. It's a little bit complicated, maybe, but I think once we get in the groove, it should be very clear. These things will be graded for completeness. Basically, like, if you give it a good try and you are communicating with me when I respond to you, then you'll get full credit for that slip for that day. Okay. And we'll do that basically every day. All right. Homework. We will have homework. I'm planning on making a homework assignment due on Thursday, but I'm aware that spring break, Thursday is a holiday for you, so maybe, I guess that's spring break. And so I'm thinking that what we'll do instead is make it, well, I'll make the due date be Thursday, but you can turn it in on Wednesday if you like, which is, I guess, tomorrow. And the homework that I'd like you to turn in, and I'll write this in the email as well, there's sort of been two worksheets that have gone out. One on, I think they're 19 and 20. One on DCT and one on LCT. And I'd like you to turn those in. And there'll be some specific instructions. You don't turn those in to me, you turn those in to your TAs. And your TAs will, over the course of spring break, grade those pieces of work and get those scores to me. Yeah. All right, so let's see here. What else to say? we're not going to have quizzes anymore. We will have a group midterm, on April 10th. So that is the Friday after you return from spring break. So that's coming up, okay? We will have maybe, I would say 4 or 5 more lectures on new material, and then the new material will stop, and then we'll have this group midterm on April 10th. Now, be aware that this midterm, it goes quite a bit back, goes all the way back to the material that we learned about directly following the first midterm. So I think where we left off was partial fraction decomposition. Yeah, so this might include, if I recall correctly, this might include topics like partial fraction decomposition, center of mass, and some other stuff. And I'll be more detailed about what will be on that exam as the date gets closer. And of course we also have a final exam, and I don't know the details of that yet, but I do know that it will take place April 25th, 2020, okay, at 1 p.m. And that's a Saturday, which is a bummer, but whatever. So the schedule that we have. You can look at the grade breakdown. The way that I want to do it is I want pre-corona stuff to be worth 64% of your grade, and post-corona stuff to be worth 36%. So I want to make the final and midterm a pretty small amount. It's going to be worth a total of 10% of your final grade, each of those, whereas the homework and post-lecture slips are going to be worth 16%. So I really want you to stay on top of the lectures and just do the sort of basics of being a student, which is watching the lectures and doing the work, work that I ask you to do. And of course, I still reserve the right to adjust this grade computation, but only if it's in your favor. Please, if you haven't emailed me yet, and there are some of you who I could name who haven't emailed me yet or gotten in touch during this coronavirus thing, please do that. I need to hear from you. If I don't, my compunction is to sort of say that you decided to ghost. But if you have a really good reason why you can't participate in these activities, let me know, and maybe we can work something out. But if you don't say anything, there's no way for me to respond, and I'll just have to assume that you're, like I said, ghosting. All right. I think that's enough for that. If there's any questions, just as always, pop them in the chat. I'm watching the Twitch chat right now. Yeah. And if there's any questions that come up, just not during this lecture, please send them via email. All right, so I want to talk about math now, and I want to talk about a very different and new topic, and that is sequences. So let's see, is this thing going to go in focus? There we go. Sequences. And actually, these are not even themselves the main object of study that we want to sort of embark upon, or a study of which we want to embark upon. Really, we're setting this up so that we can define coherently the notion of infinite series. What are sequences? So sequences are infinite ordered lists of numbers. Now, this doesn't exactly pin down what I want to say, because, infinite can, it's sort of tricky, but infinite can mean a couple of things. But the way that I sort of want to think about it is that there's a starting point for the sequence, okay? There's a starting point, and then there's then it sort of goes off infinitely in some direction. In particular, probably the positive direction. So the way, I don't know why I'm belaboring this point. It's very simple, okay? It's a really simple concept. So what are some examples? As soon as I show you some examples, you'll know what I mean. So here's an example. 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Okay, this is the counting numbers. The first term of my sequence is 1, the second term is 2, the third term is 3, etc. Okay, that's an example of a sequence. Here's another example of a sequence. 2, 4, 6, 8, 10, 12, and you probably understand the pattern. These are the sequence of even numbers, yes? We can do the sequence of odd numbers too. The first odd number that's positive anyway is 1. The next is 3, 5, 7, 9, 11. These are all sequences. Okay. Sequence which is of great interest to mathematicians and to cryptographers. Security experts are the prime numbers. Like 2, 3, 5, 7. You have to skip 9, 11, 13, not 15, 17, yes, 19, yes, not 21, 23, yes, etc. These are the primes. Okay. There's another sequence of numbers. Well, there's lots of sequences of numbers that we want. And, you know, maybe in looking at these examples, you'd be led to believe, oh, I guess sequences always have to be whole numbers. No, it's not true. These do not need to be whole numbers here in the definition. These are just numbers. Okay. Another example of a sequence, for example, would be 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and you're probably seeing the pattern there. Okay. Another another example rather is sorry. Oh yeah. You might think then from these examples that the numbers can't repeat, but that's not true either. Here's another example of a really stupid ass sequence. 3, 3, 3, 3, 3, 3, 3. That's also a sequence. Okay. Here's another sequence. Let's see, how do I want it? Yeah, sure. -1, 1, -1, 1, -1, 1, -1, 1, etc. You see these dots that I'm writing? There's really heavy stuff actually going on inside those dots. What I'm sort of assuming when I write those dots down is that the pattern that you're sort of manifestly seeing, because you're a human being who's able to detect such patterns, continues forever and ever and ever. And that's sort of what I mean by these dots. I hope that's clear, right? That this sequence doesn't end at any particular value. And that's sort of what I mean by the infinite here, okay? Goes on infinitely using the pattern established by these first few terms. What are some other examples of sequences? Oh, here's one, which maybe I won't say out loud for now what it is, but 1, 1, 2, 6, 24. What's next? I guess 120. What's next? I guess 720. And then what's next? I don't know. I want to stop there. But you might think about what the pattern is for a guy like this. It's gonna actually, believe it or not, this sequence of numbers is going to actually play a very important role in what we do. Okay? All right. So in general now, so I want to sort of leave some room because I want to do some work with these sequences. But in general, the notation that we have for sequences is something like this. We have a sequence looking like this. So in general, we have a sequence looking like A1, A2, A3, A4, etc. Okay? And we refer to these things as being the terms of the sequence. Okay? So these are referred to as the terms of the sequence. All right? And we might write this, the same object here, in a compact notation. Okay? A compact notation which might look like this. So notation, we can write a sequence, we can denote a sequence using curly brackets. This is very common. And then I write A sub n. Okay? And if I want to indicate where n starts, I might say that n starts at 1 and then runs up to infinity. So what this means, this is extra decoration that sometimes isn't supplied. But what this suggests is that what we have here is again, a sequence of numbers. This index, what we call this n here, an index, this index starts at 1 and it clicks through the positive numbers until we hit infinity, whatever that means. But I mean, what that means is that the sequence is endless. Okay, so the first term is A1, the second term is A2, third term is A3, etc. Occasionally, we might find it convenient to, instead of starting the index n at 1, we might find it convenient to start the index at, let's say, I don't know, some other number. So a very common thing, for example, is you might have a sub n where n runs starting from 0 to infinity. For example, computer programmers in many different languages might prefer this notation or this setup for sequences, because a lot of times when you're dealing with programming languages like C or like Python, indices start at 0, right? If you want to capture the first element of an array or a list, that's indexed by the number 0. Anyway, what this looks like is A0, A1, A2, going upwards, etc., infinitely. All right? And you can start this n anywhere you want. Okay. This should be actually feel familiar from stuff that we did with like Riemann sums and things like that. It's the sort of same idea. There we had an index of summation, and here we just have an index to capture the various terms. So what does this look like? Well, what we can do is specify in a really compact way sequences. So an example would be something like this. If we had the sequence n squared, okay, from n equals 1 to infinity. You can probably guess what the sequence does. What it does is we take start with n equal to 1, we shove that into n squared, we get 1, because 1 squared is 1. Then we click n up by 1 to get n equal to 2. We put that in, and we get our next term of the sequence, which is 4. Why 4? Because 2 squared is 4. Then n equals 3 gives us 9, because 3 squared is 9. N equals 4 gives us 16, 25, etc. And that keeps going up and up and up. Okay? So that's an example of sort of compact notation for a sequence. Right there. You could also have, for example, so we could have something like, how about if we look at -1 to the n over n squared. Let's start n now at 1 and run to infinity. This might look weird. We understand what's happening with the n squared, right? We just did it. It's 1, 4, 9, 16, 25, etc. But maybe more exotic for us is the -1 to the n that we see upstairs. But now let's think about what -1 to the n, what its behavior is. Huh? Its behavior is that when n is odd, so like when n is 1, for example, what is -1 to the nth power? Well, it's -1 to the first power, but that's -1. And when n clicks up to 2, what is -1 to the n? Well, it's -1 squared, which is +1. And -1 cubed is -1. And -1 to the fourth is 1. And -1 to the fifth is -1, etc. And what you see is the pattern that for odd indices, for odd values of the index, -1 to the n is -1. And for even powers of the index, -1 to the n is +1. This is important, okay, because this -1 to the n gadget is going to be extremely useful for us in the future, so make sure you understand that point. Good. So if I write down the terms of the sequence here, what I get is, what do I get? So when n is 1, I get -1 upstairs and 1 downstairs. That's just -1. When n is 2, I get 1 fourth. When n is 3, I get -1 ninth. When n is 4, I get, I didn't screw up. 1 to the 16th. If we keep going, the next term would be -1 to the 25th. The next term after that would be 136th. The next term after that would be -1 to the 49th, etc. Dot, dot, dot. because it never stops. Okay, is this clear? I hope so. So now what I want to do is take this idea of compactly expressing a sequence using this notation that we have for sequences and write down such expressions for each of these 1, 2, 3, 4, 5, 6, 7, 8 different sequences, okay? If this was class, if this was an in-person class, what I would say is, okay, now work on this, okay? Try to figure out an expression for all of these different sequences in terms of this new notation that we have. But because this isn't class, maybe what I could ask is that you pause the video and give it a shot. So do that now if you haven't. So in looking at this first sequence here, how can we express it using this notation over here? Well, I think it's pretty straightforward. I hope it's straightforward for you. This is just n, where n runs from 1 to infinity. Okay? Does this make sense? How about this next one down here? So these are the even numbers, right? How can we express this sequence using this kind of notation? 2n, where n starts at 1 and runs to infinity again. How about this third one? Well, those are the odd numbers, yes? And what are odd numbers? Well, I mean, maybe if you compare it to the line above, what you notice is the pattern that each of these numbers, 1, 3, 5, 7, 9, etc., is just the numbers above subtracted by 1. Yeah. So this is, in fact, 2n minus 1 from n equals 1 to infinity. Yeah, very good. Thank you. How about this crazy one here? These are the prime numbers, okay? 2, 3, 5, 7, 11, 13, 17, 19, 23. And if you were able to find a compact way of computing these efficiently, you would take over the world. Okay, so I'll just say it like this. This one is very mysterious, all right? There do exist, I believe, what are called closed form formulas for what the nth prime number is, but that is a topic that is way, way beyond the scope of this class, despite it being super interesting. Yeah. For people in the know, I guess, the importance of prime, if you are ignorant and you don't understand why prime numbers are important, that's fine, but just realize that so much of our society depends on the difficulty in figuring out what whether or not, for example, a number is prime. And that's directly related to, of course, the writing down this sequence sort of exhaustively. Yeah. How about this next guy? So yeah, I'm just going to leave this as a question mark. This is heavy-duty stuff, right, when you start asking questions like this. How about this one? Well, this one is just 1 over n, where n runs from 1 to infinity. Okay. How about this one? Always 3. This is just 3. That's not a 3. I don't know what I did there. 3. I think I got used to writing the curly braces, and that sort of just kept happening. N equals 1 to infinity. Okay. How about this one? Well, we kind of talked about this. This is an alternating sign gadget. Very useful. What this is, as we discussed, is negative 1 to the nth power. N running from 1. A lot of times this this decoration that we put here is sort of extraneous and will be left off, but sometimes it's useful. Okay, and finally we have this sequence down here. Well, so this sequence is very special. It has a special name. These are called factorials. Okay, and the notation is an exclamation point. So let me be clear. This number here is the same thing as 0 factorial. This number here is the same thing as 1 factorial. This number here is 2 factorial. This is 3 factorial. This is 4 factorial. This is 5 factorial. And this is 6 factorial. Sometimes, like if you're talking to a computer scientist, they might pronounce this, like, for example, 0 bang or 5 bang. I've heard that before. But I say factorial. I don't know why I prefer it. I don't have any strong preference. What is it, really? What is it? Okay, so let's see. Where's a good place to write the definition here? Maybe I'll write it up here, okay? So n factorial, okay, is simply the product of the first n positive whole numbers. The product. First n positive integers. Okay? That's what n factorial is. And I know maybe it seems arcane, but it's actually very important for us. It will play an important role for us. So it's best to introduce it now. We will take it up again later, for sure. So this is n factorial, product of the first n positive integers. That's just what it is. And here are the first 6 terms. Oh, and I should say, I guess, by definition, 0 factorial is equal to 1. This is by definition, and there are really, really good reasons why we do this. You might ask, well, what the hell do we mean by the product of the first 0 positive integers? Well, in some sense, an empty product is 1. That is to say, a product of nothing should be 1 in some sense. I don't know if that makes sense to you. It makes perfect sense to me, but you might think about why that's so. But yeah, 0 factorial is 1. And notice, do I want to make this point right now? Maybe one fact that you could think about when it comes to these factorials is that if you think about what n factorial is, well, what it is you can take n, and that's just n minus 1 factorial. So this sometimes leads to what's called a recursive definition for this sequence, but maybe I won't sweat that too much, okay? Recursive sequences are very interesting and useful in and of themselves. Recursion is a really super heavy idea, important idea in computer science and in the study of algorithms and stuff like that. But for the purposes of a calculus class, I guess recursion isn't going to come up too often. So maybe we'll forget about that. And if you don't know what the word means, that's okay. Don't worry about it. In any case, what we have then is that this sequence we can denote in the following manner that everybody in the world will understand. This is not like a parochial kind of notation, okay? This is something that is in wide usage all across the world. And what this is n factorial from n equals 0 to infinity, okay? We're starting at 0 because we see this 1 here. Does this make sense? All right, so that is, those are sequences there, and hopefully we can understand what's happening. All right, what to say? Well, what we're going to be very quickly diving into is the notion of convergence and divergence of sequences. Yeah. So let's write some definitions, I guess. What do I want to say? Convergence and divergence is convergence / divergence of sequences. So, well, let's see here. Oh, what? What to say? Sorry. So, given a sequence, and remember for us, it's an ordered list of infinitely many numbers. So it's like a grocery list, right? With infinitely many items on the list. Okay, but it's ordered. Okay, so the ordering of the numbers really matters. That's sort of what I mean by that word ordered. Sorry, sometimes I take these kinds of words for granted. So given a sequence a sub n, let's say, I don't know, n starting from 1 to infinity, for example. Okay, we can examine the limit. And this is how this is written. The limit as n approaches infinity of a sub n. Gosh, this isn't focusing all that well. Okay, there we go. All right. So what do we mean by, so notice the notation. I did not write the curly brackets and junk. What these things here then are real numbers, right? This is the nth term in this sequence here. This is the nth term of this sequence. And then what we're going to do is let n run out to infinity of this a sub n. All right? And sometimes this limit exists, and sometimes it fails to exist. Now, the sort of informal definition of a limit in this context, which probably all of you have sitting inside of your head, is that the sort of informal definition. The informal definition is that the limit as n goes to infinity of a sub n is the number L that a sub n gets closer to as n gets larger and larger. Okay? That's what it is. Now, this is an informal definition because it's kind of hand-wavy, but this informal definition is like the definition that all, that basically every mathematician or whatever has lurking inside of in the back of her or his head at all times, right? There is a more formal definition. I can state it, and maybe I'll just say it out loud, but it's not a definition that we are going to put into practice, not really. Okay, and here's the more formal definition. The limit as n approaches infinity of a sub n is equal to L if for every epsilon greater than 0, there exists a positive integer m, such that if n is greater than m, then the distance between a sub n and L, the distance, so that is to say the absolute value of a sub n minus L, is less than epsilon. That's the definition. Now, epsilons probably are giving you a panic attack. I understand students don't like that letter, and that's okay. But just know that this is sort of a hand-wavy definition, that there is a more firm definition. And if you're super into the firm definition and you want to use it, by all means, go ahead. But what we're going to do is be much more informal with the concept of limit, particularly in the context of these sequences and series. Okay. Now, so for example, let's just look at an example. We could look at the limit as n approaches infinity of, say, a sequence like 3. Okay, so I'm going back now to the sequence here, 3, 3, 3, 3, 3, 3, 3, 3, 3. Yeah? The limit as n approaches infinity of 3, you'll be shocked to know, is 3. Okay? And so we say that the sequence converges. I'm sorry, I forgot to write that. Maybe I'll write that over here. So if the limit as n approaches infinity of a sub n exists, then we say the sequence a sub n is convergent. If not, then it diverges. All right. So here's an example of a convergence sequence. So this implies that 3 as a sequence converges. And we might even say converges to 3, just to be more descriptive. Okay. Here's another example. Limit as n approaches infinity of 1 over n. So when you see this, what you should be thinking is, okay, this is a sequence of numbers. It's like 1, 1/2, 1/3, 1/4, 1/5, etc. And what is that? What value is that getting closer and closer to as n gets larger and larger? I think you know that this is 0. Or I hope you know that this is 0, right? Because as n gets larger, this denominator here explodes in value, while the numerator just stays a dumbass 1, right? So this limit is 0. And so this is the statement then, that 0, I'm sorry, that the sequence 1 over n converges to 0. Okay? How about something more complicated, though? How about something like this? The limit as n approaches infinity of, I don't know. How about something like n squared plus 3n plus 2 divided by 2n squared plus 5n plus 8. I'm just making stuff up, okay? How could we attack this? Well, I want to sort of give you 2 ways to think about what's going on here. One thing that I could tell you about are is a way of interpolating the sequence, okay? We have a sequence of numbers here. What we can try to do is, again, interpolate these numbers using a real valued function. All right, so let me define something. So a function, and remember what a function is for us in this calculus sequence. A function is it's a function which eats real numbers and which spit out real numbers. Now that's an impoverished view of the general concept of function, but it's the concept of function that we always use in this class. Okay, so a function f is an interpolating function. Or let me say it like this, is an interpolation of a sequence a sub n if it is the case that f of n is equal to a sub n. Okay? This is what we call an interpolating function. It's a function which when you shove the value of the index into f, you get the nth term of you get a term of the sequence. Okay, so for example, if you're looking at 1 over n, this sequence, then an interpolating function for 1 over n would be 1 over x. F of x equal to 1 over x, I should say. Okay, and here's the theorem that I could say. So if f is an interpolation of the sequence a sub n, then, and if the limit as x goes to infinity of f of x is equal to L, okay, so this limit here exists and is equal to L, then what you're allowed to conclude is that the limit as x goes to infinity of a sub n is also equal to L. Okay, so this is the theorem here that you might find useful. Why might you find it useful? I have a couple comments to say about this. Why might you find it useful? You might find it useful because you can bring to bear techniques that you learn for computing limits of functions, in the calculus sense, functions. Like, for example, a big one is L'Hopital's rule that we learned. Yeah, you might be able to use L'Hopital's rule in the service of computing the limit of a sequence. So that's the first comment I want to make. The second comment I want to make. What is this? Please notice this is an if-then statement. Okay, so suppose f is an interpolating function for the sequence a sub n. If the limit of the function exists, then the limit of the sequence exists and is the same value. Okay? But a big question is why this is an if-then statement and not an if and only if statement. That is to say, is the converse of this statement true or is it false? What do you think? Is the converse of this statement true? Now, what do I mean by the converse? Is the following statement true? Here's the statement. Is it true that if the limit as x approaches infinity of a sequence is L, does that imply that the limit as x goes to infinity of an interpolating function is equal to that same value L? True or false? Well, probably you should realize that that's false. Because if it was true, I wouldn't be writing an if-then statement. I would be writing an if and only if statement. Okay? You agree? I hope you agree. So what I want you to do as part of this lecture, this is the post-lecture slip thing that I'm talking about right now, is I would like you to tell me, give me an example of a situation in which the limit is, oh, sorry, I messed up. The limit is n goes to infinity of a sequence a sub n is equal to L, but the limit as x goes to infinity of an interpolating function for that sequence is not equal to L. What do I mean by not equal to L? What I could mean, and this is a hint, is that it doesn't even exist, this limit. So I want you to think hard about that and send me an explanation via email. Now, you don't have to take any photos of anything. You can just write down in the email text what is going on there. Okay? But that's the post-lecture slip. You got me? You understand what the question is asking? You know what? Actually, what I want to do. Forget it. Sorry. I don't know what I'm doing. Okay. So forget it. But if you want to answer that question via email, please do. But maybe that's a little bit too tough here at the start. Okay. I'll give you a different problem in about 10 minutes. I've got about 6 minutes left to go. In any case, I want to use this sort of idea maybe over here in talking about this limit. Somebody asked in the chat, interpolating means similar, right? I would not say that. The word interpolating, I would say, the way I think about interpolating is you're given, so let's say you're given some discrete set of data. So can you see these dots that I'm drawing? All right. So maybe you have a sequence whose values bounce around in this way, right? Like maybe this is n equals 1, this is 2, this is 3, etc. And you could plot the values of the sequence in this way as, whatever. So what an interpolating function would be, interpolating would mean that we are defining a function which connects the dots, okay, in some way. So one way of connecting the dots, for example, would be like this. So this is the graph of a function, right? And it's an interpolating function. Why? Because when you plug in 1, 2, 3, 4, or 5 into the function, what you get out is the values of the sequence at that index. Does that make sense? And again, is this the only interpolating function? No, right? There's lots of different possible interpolating functions. So here's another one, right? Equally good. There's another interpolating function, right? It's very different. So maybe this is a big hint as to why the converse of this statement that we just talked about is false. Okay. but let me finish this. Sorry. So one way we could attack this problem, okay, is to convert this, to rewrite this in terms of an interpolating function. This limit is equal to, assuming the limit exists, the limit is x goes to infinity of x squared plus 3x plus 2 divided by 2x squared plus 5x plus 8. And then we could use L'Hopital's rule or whatever. But a simpler way of going about doing this, I don't like doing it. A simpler way of doing it is just to work with this in a straightforward way and just kind of use your common sense. And we've done this before, and we'll do it again, and we'll do it again and again. So make sure that you understand what's happening. This is a rational expression in n. So we're going to factor out the highest degree term in the numerator and denominator to get that this is equal to n squared times 1 plus 3 over n plus 2 over n squared divided by n squared times 2 plus 5 over n plus 8 over n squared. Y'all follow? That's just basic algebra, right? But now the sweet thing is that this n squared and that n squared annihilate one another, okay? And furthermore, what we know, for example, based on the logic or the argument that we gave for the previous limit, what we know is that these terms here all also die. What do I mean? I mean that when n gets larger and larger and larger, because the denominators are going to infinity, while the numerators are just saying dumbass numbers, finite numbers, the entire expression, all these expressions have to go to 0. And so what do we see left over? What do we see surviving the carnage of n going to infinity? What we see surviving the carnage is the 1 in the numerator and the 2 in the denominator. So what we can learn is that this limit is equal to 1/2. In other words, this is a convergent sequence, and what does it converge to? It converges to 1/2. Does that make sense? Okay, so here is the slip that I want you to answer for me. The question that I'd like you to answer for my slip. For real this time. All right. For real. For real this time. Slip. And maybe I should encode this slip. We're going to, well, no. You're just going to reply to the email that I send out to you. Okay, so yeah. This is the slip that I'd like you to do for today's lecture. Tell me, what is the limit as n approaches infinity of, how about this? The square root of 3n cubed plus 5n divided by 12 times n plus 1 cubed. I don't know what I'm doing. I'm just making something up. So look at that right there. And what I want you to tell me, maybe I'll give you a hint. This is a convergent sequence. We'll talk more about divergent sequences tomorrow. I guess all of the examples that we gave were convergent, right? But I'm running out of time. So these are all convergent sequences. But tomorrow we'll talk about divergent sequences. And we'll start talking about infinite series. But today, what I want you to do is tell me about this limit here. Okay. So what I want you to do is tell me what the value of this limit here is in an email. Okay. And I want you to show me work. Okay. So that you're not just like, hey buddy, you're not just texting your buddy and harvesting the answer from them. I want you to show me the work, okay? Show me what it looks like. And I want that before the end of day today. All right, well, I just hit 50 minutes in this lecture. I'm going to end this thing now. I'm going to open up a Zoom meeting. I will send out the Zoom URL via email. And if you have any questions about today's lecture or about previous exercises, which I might have assigned for homework or whatever, please come into that Zoom meeting and let's chat. One other thing, don't forget, the homework, which is those worksheets 19 and 20, those will be due tomorrow. Okay, and I'll tell you a bit more about how to turn those in, how to submit those tomorrow. Okay, but just get it done by before, let's say, I don't know, midnight tomorrow. All right. Take it easy, y'all. I love you all very much. I hope you all are well, healthy, and all of that, and that you're not making other people sick. Bye.